Welcome back everyone. In this lecture, we will see how to write the character of irreducible representation of SLN in terms of semi-standard Young tableaus. So, to be actually consistent with the literature, so what we are going to do, so we are going to assume the rank of the Lie algebra to be n minus 1. So, indeed we will be working with SLN instead of SLN plus 1. So, this is just because we want to consider symmetric polynomial in the variables x1 etc. xn. So, you take SLNC. So, this is going to be a traceless n by n matrices. So, now we will actually identify Cartan here in terms of the standard basis. So, which is as diagonal matrices. So, this is going to be the span of summation some ai ei I range from 1 to n such that the summation ai should be 0. So, now the dual again can be realized as a span of epsilon I in epsilon I basis. So, this is span of epsilon I where I range from 1 to n with the relation that epsilon 1 plus etc. epsilon n is exactly 0. So, we will be working with this epsilon I basis. So, for that purpose we are going to only consider SLN instead of SLN plus 1. So, with that remark, let us actually define what is symmetric polynomial, and then we can view this character of any finite dimensional irreducible representation as a symmetric polynomial in the variable e power epsilon I. So, that way if we view, then it will be like easier to write down that polynomial in terms of the semi-standard Young tableaus. So, let us see what first of all semi-standard Young tableau, and then how to actually write given this character of finite dimensional irreducible representation in terms of this weights of the semi-standard Young tableau. So, before like moving further, let us actually define some terminologies. So, we have the symmetric group, which is the while group. So, this is the symmetric group in n letters. So, naturally this symmetric group acts on our acts on the polynomial algebra. So, you take finitely many variables x1 etc. xn, and then look at the polynomial algebra generated by this x1 etc. xn. So, now Sn acts on this polynomial algebra by permuting these variables. So, if we take for example, so let us use this shorthand notation. So, if we use this shorthand notation for given alpha, which is inside z plus power n. So, we denote this x power alpha by x1 power, let us say alpha is given by some k1 etc. kn tuple of non-negative integers, then x power alpha is denoted by x1 power k1 etc. xn power kn. In literature, these alphas are called compositions. So, now if we use this notation, then how this given sigma on Sn will act on this x power alpha. So, sigma acting on x power alpha is given by just you permute the variable, keep the exponent as it is, x sigma 1 power k1 etc. x sigma n power kn. So, now this is actually indeed consisting with the action that we have on epsilon I basis. So, indeed the way we want to identify xi with e power epsilon I. So, then you can easily see that x power alpha corresponds to indeed x power this k1 epsilon 1 plus etc. plus kn epsilon n using this identification xi equal to e power epsilon I. So, now if you apply sigma on x power alpha, then clearly sigma acts on this alpha. So, this becomes x power sigma of alpha, which is given by x power k1 epsilon sigma 1 plus etc. plus kn epsilon sigma n. So, now if you write it in terms of this variables, then it is clear that x power epsilon sigma 1 is nothing but x sigma 1. So, this becomes x sigma 1 power k 1 times etcetera x sigma n power k n. So, that is the action that we have on the monomials. Now, you extend this linearly to all the polynomials in C bracket x1 or x1 comma etcetera xn. So, now we can now define the symmetric polynomials to be the polynomials that are invariant under this action of Sn. So, you take this polynomial algebra, look at the fixed point elements under this action of Sn. So, that is given by those f inside C bracket x1 etcetera xn. So, when you permute the variables, still you get f itself. So, sigma f is given by exactly f for all sigma in Sn. So, those are polynomials called symmetric polynomials. So, now for example, let us look at this polynomial in 3 variables. So, you can take f of x1, x2, x3 to be exactly equal to x1 square x1 square times x2 plus x1 square x2 square plus x1 square x3 plus x1 x3 square plus x2 square x3 plus x2 x3 square. So, now you can easily see that this is indeed symmetric with respect to the variables x1, x2, x3. So, by permuting sigma, given sigma in S3, the variables x1, etcetera, x1, x2, x3. So, that polynomial is not going to change. So, sigma of f is equal to f for all sigma in S3. So, that is easy to verify. So, once you verify that, then it is clear that this is indeed symmetric polynomial in the variable x1, x2, x3. So, now if you take this ring of symmetric polynomials, so this is indeed algebra over C. So, it is indeed a fact that this can be generated using this elementary symmetric polynomials. So, we are not going to prove all these things due to time constraint. So, I am going to state some of the facts about this symmetric polynomial algebra. So, here is the fact 1. So, one can define what is called this elementary symmetric polynomials. So, the elementary symmetric polynomials, they are defined to be using that you can take the variable the polynomial t minus x1 times etcetera times t minus xn. So, this you can write it as a polynomial in t with the variable with the coefficients coming from this polynomial algebra C x1 etcetera xn. So, now it is not that hard to prove that this product t minus x1 etcetera t minus xn, this is indeed invariant under the action of Sn. So, one can easily prove that by permuting the variables x1 etcetera xn using any permutation, you are going to get the same polynomial for all sigma in Sn. So, using this you can easily see that this implies if you write this polynomial, let us call it p of t. So, this p of t you can write it as some summation, some coefficients e I t power I, where I ranging from 0 to n, where with the sum sign. Okay. So, exactly the sign will be minus 1 power I. So, now using this sign you can easily see that this E I is nothing but E I of some x1 etcetera xn, which is a polynomial inside C bracket x1 etcetera xn. Now, using this observation that this polynomial p of t is invariant under the action of Sn, tells you that all the coefficients must be invariant under the action of Sn. So, that tells you that all these EIs, they are all symmetric polynomials. So, now what will be like, for example, E1. So, E1, sorry, so I should write it in e power n minus I. So, E0 is exactly 1. So, that is just a coefficient of t power n, and E1 is nothing but the coefficient of t power n minus 1. So, that is indeed given by, if you just take the multiplication, you can easily see that. So, it is going to be x1 plus etc. plus xn. For example, when n equal to 2, you have t minus x1 times t minus x2, which is given by t square minus x1 plus x2 t plus x1 x2. So, you can easily see that so this is invariant under the action of S2, the coefficients. So, now you can actually write down what will be the EI symmetric, ith symmetric polynomial. So, these EIs are called elementary symmetric polynomials. So, these are called ith elementary symmetric polynomial in the variable x1 etc. xn, and I will leave it to you to write down the expression for EI. That is not very difficult. Now, what is the fact? The fact 1 indeed says the polynomial, this symmetric polynomial algebra, the C bracket x1 etc. xn, which is indeed polynomial algebra in this E1 etc. En. So, this is not very hard to prove. So, I will leave it as exercise. So, now you can see that the set of symmetric polynomial, it is indeed really huge algebra. Okay. So, if you take any polynomials in E1 etc. En, that will be definitely symmetric with respect to Sn action. So, one containment is easy to prove, but the other way you need to really check. So, that I will leave it to you. Now, let us consider this partition. So, integer partition with at most n parts, let us call it lambda. Okay. So, an integer partition with at most n parts. So, it is defined to be lambda, which is a tuple lambda 1 etc. lambda n, such that each lambda I being non-negative. So, lambda I is non-negative integer for all I from 1 to n, and the second condition, it should be non-increasing, it should be weakly decreasing, lambda 1 greater than or equal to lambda 2 greater than or equal to etc. greater than or equal to lambda n. So, now I will leave it as exercise. It is not hard to see that if I take some element lambda in the dominant lattice, dominant weights lambda plus. So, then you can write lambda in terms of the omega I basis. You can write it as a1 omega 1 plus etc. plus a n omega a n minus 1 omega n minus 1. So, because we are working with SLN, so the rank of the Lie algebra is n minus 1, which is the dimension of the Cartan. So, now using this identification, omega I is nothing but epsilon 1 plus etc. plus epsilon I on H star. You can easily see that lambda corresponds to a weakly partition. So, one can actually associate this lambda with some partition, integer partition with at most n parts whose nth term is 0. So, like lambda 1 greater than or equal to etc. greater than or equal to lambda n minus 1 greater than or equal to 0. So, the way we do it, you write lambda in terms of epsilon I basis, and then you take the corresponding coefficients of this epsilon I and arrange it in the decreasing order. So, now you can easily see that lambda must be a1 epsilon 1 plus a1 a2 epsilon 1 plus epsilon 2 and so on, plus a n minus 1 epsilon 1 plus etc. plus epsilon n minus 1. So, now if you take lambda and then write it in terms of this epsilon I basis, you can see that this is given by a1 epsilon 1 plus a1 plus a2 a1 plus a2 plus etc. plus a n minus 1 epsilon 1 plus a2 plus etc. plus a n minus 1 epsilon 2 and so on, etc. a n minus 1 epsilon n minus 1. Now, we will think epsilon n coefficient being 0. So, then it is clear that, so lambda corresponds to lambda 1 being a1 plus etc. plus a n minus 1, lambda 2 being a2 plus etc. plus a n minus 1 and so on. Lambda n minus 1 is a n minus 1, lambda n is 0. So, this is the partition that you get starting from lambda being dominant. So, we will always identify any dominant weight with this corresponding partition. So, then we will work with that. So, given lambda, we take this corresponding partition lambda 1 etc. lambda n minus 1 0. So, this is the partition. This is another way of indexing the dominant weights of SLN in terms of partition. So, now we will use this notation in order to define the semi-standard Young tableau and corresponding Schur polynomial that is associated with this semi-standard Young tableau. Now, so we have this integer partitions. So, given these integer partitions, so we have we can naturally represent that integer partition in terms of what is called Young diagram. So, what is Young diagram of shape lambda? So, let us just define. So, the Young diagram of shape lambda. So, this is so there is a very formal definition of this in terms of subset of Z cross Z, but let's take the more diagrammatic interpretation, which will be more helpful. So, what we will do? So, we will actually think this Young diagram as the collection of boxes arranged in left justified positions with the lambda I boxes in the ith row. So, what we will do? So, you have lambda. So, lambda is indeed partition lambda 1 greater than or equal to etc. greater than or equal to lambda n. So, now, so the way you want to think about lambda using this Young diagram. So, what is the associated Young diagram? So, the Young diagram is nothing but the collection of boxes. You arrange it as follows. The very first row has lambda 1 boxes. So, this has lambda 1 boxes. So, then you can actually start from all the way to left and then arrange this lambda 2 boxes just below lambda 1 boxes. So, the second row, so that actually consisting of, let us say, lambda 2 boxes. So, and so on, you arrange it so that, so you will have lambda n boxes at the end. Okay. So, this is called Young diagram. So, the Young diagram associated with given partition is given by this physical interpretation. So, now for example, if we take lambda to be 6, 4, 4 and 2 0. So, this is let us say the partition we have. So, then the corresponding Young diagram is going to be, so you first arrange 6 boxes in the first row, then you put 4 boxes below that, and again another 4 boxes below that, and you arrange 2 boxes below that and only 0 box below that. So, there is no box. So, 6, 4, 4, 2, 0. Okay. So, basically the number of entries in lambda is what determines the number of actually the variables. Okay. So, if it is n tuple, if lambda is n tuple, then we are working with the variables x1 etc. xn. So, there are n variables. Okay. So, now what is this semi-standard Young tableau? So, the semi-standard Young tableau, okay, associated with the lambda. So, this is indeed a collection. So, in this collection what we will do, we will actually start filling this given Young diagram using this entries from 1 to n. So, such a way that each row is weakly increasing and each column is strictly increasing. So, the semi-standard Young tableau T, so this is indeed like an element here. So, let us take some A inside. So, A is a filling of this Young diagram of shape lambda. So, you take this Young diagram of shape lambda and start filling. So, filling with the what? Entries from 1 to, so entries from the set 1 to n, such that, so when you take this row, so each row is weakly increasing, and if you take each column, that should be strictly increasing. So, each column is strictly increasing. So, this is the condition that you put in the filling. So, such a filling is called semi-standard Young tableau of shape lambda, and you collect all of them, that is the set that we have here. Okay. So, this is the set of all semi-standard Young tableau of shape lambda, which is denoted by capital S, capital S, capital YT and of lambda. So, for example, let us actually do this one example. So, here is the warning. So, the number of variables that actually plays important role in filling these diagrams. So, for example, if I take the number of variables, so which is that lambda being treated as a partition with respect to, like, let us say 2 parts. So, that actually kind of determines, so because the 0 that we are including in lambda, so that actually kind of takes care of the number of variables that we are using. So, that actually is somewhat important, because that actually takes care of where these entries are coming from. So, for example, so let us take this following example. So, if we take lambda being just 2 comma 1, so then the number of variables, so that is going to be exactly 2. So, now we will take this Young diagram, so which is given by this 2 1, and we start filling it using the entries that coming from 1 comma 2. So, the entries must come from 1 comma 2. So, now given this data, if you start filling, so what is the condition? So, each row, entries in the each row is weakly increasing. So, entries in each row should be weakly increasing, and entries in each column must be strictly increasing. So, if you use that algorithm, then now you can easily see that if I start with the first box can have entry both 1 and 2. Let us say we have 1 now. So, then the second box either it can have 1 or 2. So, let us put 1 first. So, then the third entry, the below box, it should be strictly increasing. So, we do not have anything else left with. So, we have to fill it with 2. So, now you can actually fill with the second thing. So, you start with 1. So, now you can actually put 2 here. So, already we have put 1 there, and then because after the entry 1 we have to increase the column entry. So, it has to be 2 in the bottom. So, now if you go to the next filling, so we can actually start with 2 also, but if you start with 2, then the rows should not be increasing. So, it is weakly increasing. So, we can fill 2, but the problem will come when you actually come down to the bottom first column entry. So, here you can easily see that we do not have any entry from 1 comma 2 that can be filled in this box. So, that means this is actually not valid. So, there is no semi standard Young tableau starting with this 2 in the first box. So, that tells you that so only these 2 are actually possible in this case. So, the number of entries actually 1 comma 2 gives lots of restriction on this number of semi standard Young tableau. So, in case if you view this as the partition 2 1 comma 0, so then the number of variables must be 3. So, then entries actually come from this set 1 2 3. So, then you can easily see that there will be more choices for us in order to fill these boxes. So, let us take these boxes and then start filling and then see. So, if we take this box, you can see that if you think about semi standard Young tableau, that actually the very first box having 1. So, that will be having the following choices. So, if this is 1, the second entry it can be 1 and then 2 and then can be 3. So, these 3 choices are there. If this is 1 1, then you can easily see that. So, this entry must be increasing. So, it must be 2. So, that is one possibility, and another possibility is if it is 1 1, then it can be 3 here in the bottom. So, this is another possibility. Similarly, if it is 1 2, so then it can be 2 here, and similarly here it can be 1 2 and then 1 3, and here similarly 1 3 and then 2 1 3 3. These are all possibles. So, you have 1 1 2 1 1 3 and then 1 2 2 1 3 3. So, now you can also start with 2 in the first box. So, then you can easily see that the bottom box must be having 3, and then this first row second box either it can be 2 or it can be 3. So, these are all the choices that we have. Okay, so totally we have 8 9 8. So, I guess yeah, this one not yet filled. So, this is not there. So, there are 8 boxes that we will get. So, 1 1 2 1 1 3 1 2 2 1 3 3. So, this is there 1 1 2 1 1 1 2 2 1 1 3 1 3 2 1, 2, 3, 2, 2, 3, 2, 3, 3. So, all these are the only possibilities. So, now what one can do, so given this semi-standard Young tableau of shape lambda, so one can associate, so let us say T is the tableau from this semi-standard Young tableau of shape lambda. So, then one can associate this monomial associated with this T. So, this x power this omega of T, which is the monomial that we are going to associate it with T, that is going to be exactly x1 power k1 times etc. xn power kn, where ki is the number of i's that appear in the tableau T. Okay. So, for example, if we take this first tableau, then this is nothing but x1 square 2, sorry, x1 square times x2, and then this is x1 square x3, and this is x1 x2 square, and this is x1 x2 x3. So, this is x1 again x2 x3, this is x1 x3 square, x2 x3 square, and this is x2 square x3. So, now what is our sure polynomial associated with this lambda? So, given lambda, which is a partition lambda 1 etc. lambda n minus 1 0. So, we take this sure polynomial associated with this lambda. So, this is nothing but summation x power omega of t, t runs over all this semi-standard Young tableau of size lambda. Okay. So, you can easily see that just from the definition it is not very clear whether this is indeed a symmetric polynomial or not, but one can actually define the action of this symmetric group on this tableaus, that is actually will tell you this is indeed a symmetric polynomial. So, I am not going to get into the detail, I am going to just write down the result, and then I will give you the reference where you can find the details. So, for example, if I take this S and then this lambda to be 2, 1, comma 0. So, then you exactly get the monomial sums from here. So, this is going to be x1 square x2 plus x1 square x3 plus x1 x2 square plus x3 x1 square plus twice x1 x2 x3 plus x1 x3 square. Oh, sorry, I have written the same here, x1 x3 square. So, now I have written 6 terms. So, then what remains is x2 square x3 plus x2 x3 square. So, now you can easily see that these are all like symmetrically arranged. So, this is indeed symmetric polynomial in this 3 variables x1, x2, x3. So, this is indeed very clear from this very explicit expression. So, now if you actually look at only the 2 variable thing x1 s21, then you will be actually getting x1 square x2 and then x1 x2 square. So, only sum of these 2. So, that is actually again polynomial in 2 variable x1 square x2 plus x1 x2 square. So, this actually indeed tells you that if you take these zeros, that is actually kind of important, whether you are thinking the symmetric polynomial as like n variable polynomial or n minus 1 variable polynomial and so on. So, that actually determines how this polynomial looks like. Okay. So, one should be little bit cautious and then while writing down the polynomial. So, here is the theorem, so which I am going to just state it. So, the best reference for this is a Stembridge paper on a concise proof of Littlewood Richardson coefficient. Okay. So, that actually is just 3 pages paper, you can actually find this proof of this. But I am not going to do it in this case because of the time constraint. So, what is the theorem says for lambda which is dominant. So, you write lambda as a partition, lambda 1 greater than or equal to etc., lambda n minus 1 greater than or equal to 0. So, then if you take this symmetric S of lambda summation x power weight of t where t runs over the semi-standard Young tableau of shape lambda. So, this is exactly the character chi lambda. Okay. So, this is indeed true. So, this actually gives very explicit expression of this chi lambda in terms of this combinatorial model called semi-standard Young tableaus. So, this is indeed a very important theorem that actually expresses the character in terms of the combinatorial data. So, now using this one can actually talk about the stability and so on very easily. For example, let me just state one of the important corollary of this theorem. So, if you take the product of two different Schur polynomials, so let us call them chi lambda without any confusion. So, then they are indeed character of the representation that tensor product of the corresponding irreducible representation. So, once we think this as character of this tensor product of two representations, then using this complete reducibility or Weil's theorem, we know that this tensor product can be written as direct sum of finite dimensional irreducible representations of SLN. So, in particularly this can be written as summation some chi gamma where the coefficient C gamma lambda mu with the coefficient C lambda mu gamma, where this gamma runs over the dominant weights. So, now this C lambda mu gamma is indeed non-negative integers. So, these are called what is called Littlewood-Richardson coefficients. So, what is the corollary? The corollary says if you take product of two Schur polynomial, okay, if you use this semi-standard Young tableau definition, it is not at all very clear from the definition that why the product of these two polynomials should be non-negative linear combination of again Schur polynomial, and that indeed comes from representation theory. Okay. So, one can actually straight away prove that and that proof indeed going to give you how to compute this LR coefficients, but that also you can find it in the Stembridge paper on this consensus proof of this Littlewood-Richardson rule. Okay. So, but this is something like one is using representation theory in order to prove something in combinatorics. So, which is not at all obvious. So, once we know this, then we can attempt to actually calculate what will be this coefficient, but even that I am saying like non-trivial thing that follows from representation. Okay, I will stop here and I will actually take one more half an hour lecture and then explain the BGZ resolution and then how to get or interpret Weil character formula using the BGZ resolution, and after that we will stop. Okay, thank you very much. We will see next class.